Okay, we defined conditional probability in the previous video. Here, in the second example, I'll give you another example with real data. So the research question we are going to consider is the relationship between smoking and cholesterol problem. So does smoking increase the risk of high cholesterol or not? Okay, so maybe most of you are young, so at your age, you may not worry about your cholesterol, but in your 40s, like me, you are going to start worrying about cholesterol. You are going, if you see a doctor, definitely they are going to tell you like your pressure, blood pressure, cholesterol, glucose, to worry about that. Anyhow, it's a serious problem. Uh, so we'll see this in from data. Our data, the data I'm going to show you is from National Health Interview Survey, NHIS data from 2018. So this data is annual. So every year they maybe every year, every other year they publish interesting data about medical and health related questions. And see, I take only two variables: whether a person is prescribed for high cholesterol, and the other variable is whether that person was ever smoked or not. Okay, so we have only two variables, but in the original data, if you are interested, there are really various categories and very interesting data. So it's pretty interesting data to have a look at if you're willing to do a research. Anyhow, back to the data. We have two columns, and we have, look at this number, 7,889, because the first row is variable name. Taking -1, we have 7,888, right? Nearly 8,000 observations. 8,000 observations are in our data, and one observation is one person, right? So again, imagine the underlying experiment. You randomly choose a person and ask about, observe he or her, like his or her, like medical status and smoking habit. Okay, so then I will denote smoking as S and H for high cholesterol. Okay, and then my first question, basically we would like to test if smoking increases the risk of high cholesterol. Okay, using our notation, what probabilities do you need to compare? Right? So typically this is the most important question and where most students fail to get correct, right? So it is easy to calculate this probability. I told you how to do it, just it's automatic, mechanical algebra. But what's more important in your research and your application is definition of the question, right? Translating your research question into statistical framework, statistical notation, statistical model. So here, which probabilities you need to compare? It's very important question. So definitely try this. Think about this before turning to the next one. See the answer. So then, what you are going to do here is you are going to compare the people who smoked, and versus the people who never smoked, right? So that means in your first experiment, you are going to choose from those who smoked, and in the other experiment, you are going to choose from those who never smoked and compare their probability of high cholesterol. So conditions are different. Condition is based on smoking record, smoking history, and then main event, the probability will be attached to cholesterol. So the answer is C. This is like, interpret this as probability of having high cholesterol if you smoked versus probability of high cholesterol if you have never smoked. Exactly, that's what we want. So it's language problem. It's about interpretation. How can you interpret our casual language to statistics? Okay. So this is the answer. You have to compare them, and then we are going to calculate those conditional probabilities from our data, real data, and the technique is the same. We are going to use pivot table again, right? So we have done this in chapter 1, and as I said, this is really important to do pivot table. So you get empty table, so you have to choose variable, like bring one to column, and put any variable to values. So here, get this. Now, as a default, you get count frequencies. By the way, you see blank because the area I chose include like the rows beyond observations. So these rows are counted as blank. So there is just blank. Well, I don't need it. So then in this case, you will just click it off. Similarly, let's click it off. Like so, now you have the frequency distribution table out of more than 7,000. Like say, nearly 3,000 have like so. Row is like this is high cholesterol. Yes to high cholesterol question, and this is no to smoking question. So have never smoked but has a high cholesterol. That's more, like nearly 3,000, and another 3,000 have high cholesterol and have smoked before, right? So this is the first step, and second step, we are going to convert the count frequencies into probability. So see here value field setting and show values as probability, right? So this is the probability of 4 different outcomes, right? Excuse me. Never smoked and no high cholesterol, and smoked before but no high cholesterol, never smoked but has a high cholesterol, and smoked before and has a high cholesterol. So there are 4 different types of people, and we obtain probability for each of them. And if you add these 4 numbers, it should be 100%. Okay, but this is unconditional probability. So their denominator, each probability is calculated based on the whole sample. The denominator should be 7,888. But what we want is, back to slides, we would like to impose some condition when you calculate the probability. Okay? That means, so first think about probability of high cholesterol given smoking. Okay? So then high cholesterol is here, smoking is here, because column is about smoking variable and row is about high cholesterol variable. So anyhow, you are going to restrict your data to this column and calculate how many of them have yes here. Out of these 2, how many are here? So we are going to calculate probability within here. And similarly, when you calculate probability given never smoked, you are going to use the other column. The other column will only include those who never smoked. So this is the condition of S complement. And to calculate the conditional probability for each condition, it's actually easy. So back to here, value field setting, And I am going to go here. Instead of percent of grand total is 7,888, but we are going to use denominator percentage of column total. This is exactly how we calculated conditional probability in the first video, right? So like this. So if you use this column includes those who have smoked before, and then among them, only 19% has no high cholesterol problem, but more than 80% have high cholesterol. But those who have never smoked, like 70%, have high cholesterol, and 28% don't, right? So this is how you utilize pivot table function on Excel to calculate conditional probability easily. Again, this is unconditional probability, joint probability distribution. But what we need is, to answer our research question, what we need is not joint probability or not unconditional probability, but conditional probabilities. So that's how we do. That I just showed how you can do that on Excel. But if you wanted to calculate that from the joint probabilities, the idea is the same actually. You can do the same thing. So we have these numbers. From the joint probability distribution, same thing. When you calculate condition on S, delete the other side. Delete S complement, second column, and just look at these numbers. Even though they are probabilities, not number of observations, still does not matter. You may use them as if they are just observations, number of observations, because probability is basically based on frequencies. You may directly use that to calculate the conditional probability. In the end, it is 80%. Okay. So from here, you can see that and 80.11%. Let's check it. Right, same thing. Yes or order of yes or no is different. Just in case if you want to change the order, like no comes first because alphabetically no is first, but you may change it like this. Sort Z to A. Then you may change the order of yes and no. Then you get 80.11% as a conditional probability. That's exactly what we get here. Okay, so it does not matter. And at this point, we can make another formula. Previously, I used frequency, just number of observations. That was more intuitive, but it doesn't matter even if you use just probability instead of count, right? Not a problem. In the end, they are the same conditional probability. Okay, so if you use a formula to calculate conditional probability, use either. They should be the same. Okay, now then it is your turn to calculate the other conditional probability. So I believe it's I actually already showed you the answer in Excel, but try this by yourself. Or you may calculate probability, conditional probability from these numbers, or you may open the Excel file and try the pivot table function by yourself to answer this question. Right? It's up to you. I'll be waiting here. So stop the video and continue when you are done. Okay. Okay. Let me turn the page. The answer is 71.3%. So S complement is the condition. S should not happen. So never smoked. Include these two outcomes only. Okay. So you delete the first column and use the second column only. Among these two types, we are calculating probability of high cholesterol, the first row. So out of these two, what is the proportion of 37? Right? So numerator is 37. Denominator includes two types. Okay? So formula is like this, but just without formula, it is easy to understand what is going on. That is like this. So then, as you can see, probability of high cholesterol if you smoke, if you have smoked before, is higher than the other side. If you have never smoked, it's 71%. But still, it's pretty high, right? So cholesterol is a big problem. Be careful. Anyhow, by the way, this is a real data, right? It's not a made-up data. And from this formula, so in the second example, we learned this formula, right? And it's very intuitive from this example, but we may apply the formula to obtain a new rule. Actually, nothing special. You are going to bring this denominator to the other side, multiply on both sides, then you get probability of intersection. A cap B is probability B times probability A given B, right? So how can we interpret this? This is called general multiplication rule. So probability of intersection can be written as a multiplication. It's multiplication, okay? So interpretation is also natural. You can, the left-hand side is probability that A and B happen at the same time. So they simultaneously happen, right? And right-hand side is like sequential. First, you check the probability of B first. And then when B did not happen, you don't need to keep going. You can just stop there because anyhow, if B did not happen, it is not included in the intersection, right? But if B happened, then you have to look at A then, right? So given that B happened, if A happens too on top of that, then that means A and B happened together. Both happened, right? It's sequentially, so it's like this. Imagine like this. So I am looking for some students, assistant, who got A from micro and another A from macro. So you may read both grades at the same time and see who got A in both classes. But alternatively, what you can do is you can check micro grade first. And if your micro grade is less than A, I don't care. I will just drop them. And among those who got A from micro, given that condition, I check how many of them got A from macro, right? So you may check them at the same time or sequentially. It's kind of that interpretation, like simultaneous or sequential sequential events, but that's purely just imaginary timing. On probability, you have no difference, right? Anyhow, in the end, you count only when both happen. Both conditions are satisfied, okay? And then another, it's a totally different question. Like try this. Probability of if you smoked, given that you smoke, what is the probability that you don't have high cholesterol? You are very lucky. You have no problem even if you smoked. Calculate that probability. If you have done the pivot table before for the previous question, you can find this easily, or you can use a calculator to calculate from these numbers. Either way, try this. Okay. Okay, let me turn the page. The answer is, so first, condition is S, so you delete second column. The last column is deleted, and among these, you are looking at H complement, 9.42%, 43%, excuse me. So numerator is 9.43, denominator is the sum of these two, okay? So this is what you get. This is how you calculate that, this conditional probability. Straightforward, it's 19.989. And And then you can find this is the complement of this one, which is probability of H given S, right? Back to pivot table, you see I said some of these two probabilities must be 100%, right? Because there are only two types of people satisfying the condition. So if one happens, and then the other, if one does not happen, automatically the other will happen. So it's exactly 100% total. So that means mathematically we may derive this rule. Always for any event, if their conditions are the same, then complement rule applies again. So for any given the same condition, the main event is complement, then their sum should be 100%. Okay, and that is complement rule for conditional probability. Given the same condition, one thinks about probability of something happens, and the other is probability of something does not happen. So either of them, so always 100%. The main point here is they have to share the same condition, because depending on the condition, it determines what kind of experiment you are going to think about. So when you think about the probability, you have to have the same experiment, then it's either happen or not, right? So that's the complement rule. So you have to fix the experiment, the condition, as the same event, and then the sum is automatically 100%. So this is intuitive. When you explain that in words, it is intuitive, but the main problem is the notation. Notation is confusing. The second event is condition, so remember that should be fixed. Okay, it became a long video, so I will use another example to explain another interesting topic related to conditional probability in the next video. See you there. Bye.